taking inferential statistics. So just one quick note. Um, this is a high-level overview. We're not going into the methodology of inferential statistics. This is just to give you a refresher if you've done a stats course already, and if not, just awareness of the different inferential statistics. To understand the methodology behind them, I highly encourage that you take a stats course, and it will give you a better understanding. But actually calculating things like odds or ratios is outside the scope of this course, but it is of importance when talking about quality. A couple of housekeeping items before we get into content for this week. Assignment 1 and midterm marks should now be released. If you don't see them, please let me know ASAP and we can figure that out. Also, in regards to the assignment 1 marks, I have yet to respond to emails about them. I am working my way through them. So if you haven't heard from me yet, I will be getting to your email. Other than that, reminder, assignment 2 is now out. If you have any questions, please reach out sooner rather than later about the assignment, and I can assist where I can. All right, on to course content. Okay, so now we're going to talk about the content for this week. Like I said, it's fairly straightforward. It's inferential statistics. I believe if you've taken a statistics course, this will be pretty much review for you. It's a very high-level overview of inferential statistics. It is not meant to substitute a statistics course, strictly because there is no way I could fit all inferential statistical techniques into 1 week. Okay, so essentially what I'm highlighting in this lecture is basically the use of inferential statistics within quality. In that kind of capacity, you'll be responsible, not for this course, but in kind of your professional lives, you'll be responsible for diving into the different statistical tests to understand how they work and how to interpret them. Like I said, there are a lot of them, and each one has its kind of opportune moment of use, okay? In terms of inferential statistics, these are statistics that are used to test whether the differences or the associations, basically the relationship within the data collected, if it has occurred by chance or if it's a true pattern, okay? So we often use kind of that 5% rule of potentially happening by chance, okay? We always want to be as confident as possible, but the general rule, 95% confidence is statistically significant, okay? Statistical significance talks about the findings would be unlikely to happen due to natural chance or variability within the data. So it is directly the response of the relationship between 2 or more variables, okay? We have to keep in mind that things can happen by random chance. That's just the nature of life. So what we try to do is we try to use these statistical tests to identify what is happening by chance and what is a true relationship, all right? Now, there are many disciplinary perspectives that are going to influence the selection of tests that you want to use per project, right? There's biostats, epidemiology, psych, sociology, all these different disciplines that have different viewpoints on inferential statistics. Just in terms of my own bias, I look at things from an epidemiological perspective. Okay, so my comfort zone lies a lot within correlations and logistical regressions. Okay, so that's kind of how I view things. That doesn't mean it's the only way to do things, but just from my kind of academic upbringing and my experience, that's what I rely on. Other people will prefer different tests depending on the situation. All right. Now, as I mentioned before, there are a large number of tests that will give you inferential statistics. Okay. So again, this is in no way comprehensive, and you should always refer to a stats textbook or even online. Use resources that are at your fingertips. The best one is if you either have a mentor or a supervisor. Those are usually the best brains to pick because they can also give you that firsthand knowledge, and teaching. Okay, they can walk you through the tests. Like I said, each situation is different, so each one will call for different statistical methodology. Okay, so one thing that's common amongst most, if not all, inferential statistics is the discussion of normal distribution. Normal distribution is essentially that bell curve, right? That bell-shaped curve that looks at data as it's plotted as frequencies by value, okay? This shape typically is going to arise from random variation. Now, a good way to think about this is let's look about it in the terms of academic grades, okay? Now, typically, when we look at academic grades, at least the way it was traditionally designed, I should say at least tests were designed such that the mean would lie around that 70 to 75% mark, right? So we would like to expect to see a bell curve with the peak of that bell around 70 to 75 on that x-axis, right? And then as you move left or right, the number of students achieving those marks are going to reduce depending on the direction you go, okay? This used to be a method in terms of recognizing if tests were too hard, not hard enough, fair, unfair, so on and so forth, because you could actually see through the bell curve where the bulk of students were performing based on their frequency, all right? And teachers, what they used to do, I don't know if it's still done commonly now, but they would move that bell curve of marks if the test was too tough and that mean was actually below where it should have been, especially if it was below 50 and the majority of the class failed, typically an indication of an unfair test, and the marks would be bell curved up to correspond appropriately. Now I'm not saying that to get your hopes up or anything, more so just so that you can visualize what this bell curve would look like. It's basically taking the average and visualizing how those frequencies shape out. We talk about this because often this might be a condition for using specific inferential statistics. Okay, so now we're going to talk about parametric versus non-parametric tests. So parametric tests essentially yield a statistic and a p-value, right? So that probability of happening by chance upon mathematical measures of distribution variability. So these are things like standard deviation or standard error. So we use this in some tests are unpaired t-tests, ANOVA, multiple regression, so on and so forth. Okay, like I said, refer to a stats textbook for more information on these. Non-parametric tests, what these do is they use the relative positioning of ranks of the data to yield statistical tests or statistical values and a p-value. So these are things like the Mann-Whitney U-test, Kruskal-Wallis test, and so on. So this figure is a good way to represent it. What you're doing is you're looking at essentially two samples, or I should say two groups, and you're comparing them positionally. And that's how you're going to come up with your statistical values. All right, so there's a couple assumptions we have to make for using parametric tests. So we have to make sure that essentially these things are checked off before we can dive into the world of parametric tests. The first is the variable values are interval or ratio. Okay, so we can also include ordinal data here. The next, random sampling from a defined population. Okay, so we need to make sure that the sample that we choose is done at random. Of course, you're going to have kind of selection bias every now and then, but you're going to do the best you can that you took a purely random sample. Okay, the idea here is that you're going to aim to capture data that is representative of the entire population. Next is normal distribution. So now one thing with normal distribution, so we do want normal distribution to appear. However, just keep in mind that it's not going to look perfect, and it doesn't have to look perfect to meet this assumption. However, it must be within reason. Okay, so it must somewhat resemble a normal distribution, and we'll look at examples of that in a second. Lastly, there has to be equal variances if you're going to use 2 or more groups and variables. Okay, this can be evaluated during data cleaning or during the descriptive stats phase. So kind of that first round of statistics that you're going to do, that's going to describe the sample. Okay, so here we have some examples of what I was talking about where the normal distribution doesn't have to be perfect, it just has to be reasonable. What you can see here is that normal distribution line superimposed over basically a bar graph. So you can see that the bar graphs look very different in each 3 of these examples. However, when you look at kind of the superimposed distribution, right, when we take the mean and then the standard deviation, it's relatively normal when we look at it, okay? So just keep this in mind when you're collecting your data and looking at the frequency of it, that it doesn't have to be perfect to be a normal distribution. Now, when we look at comparison and statistical significance, one of the things, and again, remember, I'm coming at this from a very epidemiological perspective, but t-tests are an excellent way to look at differences between means across groups. This is something that I have often used in my practice to look at kind of the difference, specifically when we're looking at vulnerable groups to infectious disease, okay? That being said, there are many ways to report the necessary metrics that you need. Again, it's going to depend on the study that you're doing, the variables that you're collecting. Again, this is going to sound like a broken record as we go through this lecture this week, but always refer to a textbook or your supervisor or whoever it may be, just to get kind of that second opinion. Ensure that you're using the optimal test for the situation, because while there are many ways to do something, especially with comparisons, you want to make sure that you have the most optimal way to do so, okay? Now, when we're doing an interpretation of sample characteristics, essentially what we're doing is we're reporting that sample characteristic, preferably by any significant difference between the groups, and then followed by the statistic and then the p-value. So this could be your t-test value in the statistic, followed by the p-value that was spit out, okay? Now, this assumes that you're only reporting significant differences between the groups when you follow kind of this reporting structure, okay? So keep that in mind when you use this method. Now, if we go back a couple weeks with the PIOMM model, this looks at change over time among paired samples. So a group comparing before and after intervention data. So it's essentially one group. We're measuring them before an intervention is put in place. We're putting them through the intervention, and then we're testing them again, okay? So in these common paired sample tests, typically t-test, a different form of t-test is used for these. However, we can also use the Wilcoxon signed rank test, which is a non-parametric test where we compare the ranks. Okay, so there are kind of 2 methods to doing this. Now, the interpretation of before and after comparisons, the way this works is you're going to state if and what change occurred or didn't occur, and then you're going to state whether that change or lack of change is significant based on the p-value. So remember, p-value typically we want it 0.05 or below. If it's above that, you're going to be giving it up kind of to chance, I guess, or probability that that naturally occurred, okay? Now, this is where it also gets tricky. I put this in because the textbook that we're referencing for this lecture, it had it in there. In my experience, it's been a little bit different. They're saying if there's a control group, causation may be possible to infer. Again, this comes down to your study design just as much as it comes to the statistical tests being used, okay? Now, one thing we can say, if there's no control group at all, you can infer an association or a relationship, but you cannot infer causation. All right. Again, this will kind of make its way through the study design to know when you can and cannot infer causation. All right. That's, again, kind of a combination of epidemiology and statistics wrapped into one. We could do probably countless lectures on whether or not we can infer causation in certain specifics scenarios or not. One other thing that you should do, and this is a common practice in academic reporting, you should always state alternative explanations that may have contributed to your findings. Okay, typically in research, I've seen this done in the limitations section. Sometimes it's done in the discussion, but it's not going to be, here's the results, here's the only way this can occur. Typically, you're going to want to say, this is what happened, this is why we think it happened. It could also have happened for reasons B, C, or D, kind of thing, okay? That just kind of, it's the same idea as reporting biases. You're just essentially letting it be known that you're aware that this may have happened. Now again, in terms of the interpretation between group comparisons, you're going to state if significant outcomes existed between the group differences. Remember the p-value and whatnot, and especially after intervention has been implemented. Now, like I said in the last slide, you're going to want to state alternative explanations for the findings or something that can contribute to the findings. Again, this is kind of like the biasy idea where you're just saying that you are aware that it could have happened for this reason. Because often we cannot, with 100% clarity, be sure of this one explanation. So we're basically covering all the bases by explaining all the alternatives. Now, this is another important piece of the puzzle. Sometimes it's necessary to control for other factors that may influence the results. These variables that might alter the results are called confounders. This can include, but is not limited to, age, gender, or any other collected variable. It could be a variable that you didn't collect, which makes kind of the interpretation of results very problematic. And one quick example off the top of my head. So back around, I want to say the 1960s, but when cigarette smoking was becoming popular, what was noticed was that the incidence of lung cancer was also increasing. Now, researchers wanted to set out to figure out what could possibly be causing lung cancer to increase at the rate that it was. They put out a study, and what they ended up doing was they measured variables such as like coffee consumption and incidence of lung cancer. What ended up happening was that for a brief moment of time, it was thought that consumption of coffee led to lung cancer development. What was actually going on was that the true relationship between cigarette smoking and lung cancer was confounded by coffee consumption. What was happening in this study was that, unbeknownst to the researchers, those who were drinking coffee were typically smoking at the same time. Okay, so it looked as if coffee was the cause, whereas it was truly the cigarettes. This does happen from time to time, so we have to be aware of possible confounders. Eventually, it was found out that it wasn't that people were drinking coffee and developing lung cancer. It was that the cigarettes that they were smoking while they were sitting at coffee with their friends was the reason that lung cancer was occurring. So kind of one of the other, there are criteria for causative factors. We're not going to go over them in this class or in this lecture, but it's worth taking a look at because those criteria can actually help you understand if you're dealing with a confounder or not, right? One of the mechanisms in terms of causation is there must be a mechanism for that association. So if we look at the idea of coffee consumption and lung cancer, there's really no biological mechanism to explain that. So the researchers knew something probably wasn't right there, so they started looking outside the box as to what else was going on. That led to the identification of cigarette smoking, which led to the identification of coffee as the confounder. Okay, so especially when you have a large number of variables, depending on what it is you're studying, confounders can easily become quite the problem. Now, benchmarking is an approach that is, I'm going to say, often used in quality. I've used it often in kind of the long-term care setting, specifically when I'm working, or when I did work for kind of a larger company that was overseeing many homes. And what this did was it basically let us know, okay, are we meeting the standards or are we not? Okay. Now, it helps identify kind of areas of shortfall, right? So for example, in my experience, if a number of homes were not meeting the benchmark and they were all under the supervision of a regional director, well, that regional director is going to get either a talking to, or they're going to play a closer eye to that regional director because there's some commonality going on in those homes that's causing them missing benchmarks. Okay, basically what benchmarking is, it's an evaluation approach that analyzes and compares interventions or outcomes using an established standard. Okay, so for example, if I look at, let's say, all the long-term care homes in the Durham region, I can have a benchmark of a certain number of falls, and then I'm going to start kind of looking at which homes meet that benchmark, which don't. Why do the certain ones that are meeting the benchmark, why do they meet the benchmark? What's the commonality? And I can start kind of understanding relationships in that way. Now, it does promote the development of best practice and quality improvement, and it's especially useful in evaluating outcome attainment. So like I just said, in something like meeting a standard, right? So meeting, a threshold for number of falls that are occurring, very valuable for evaluating those kind of things. Now, the interpretation of benchmarking is basically to state what significant differences occurred in the outcome after intervention. So for example, and this is straight from the book, overall, 80% of the population of interest reached the benchmark of 4, which stood for adequate knowledge for the nutrition problem. Individuals in Group E were more likely than the other counties to attain this benchmark. And then they give you the statistical significance of it, right? So it's under 0.05. It's statistically significant, okay? Now, this is an example of what it looks like. What you have is the groups at the bottom. The different lines denote different variables, and you have your benchmark set at 4, okay? And that's the horizontal line. And now this is how it looks graphically. Obviously, you can also look at it numerically. Visually, it's a good way to provide a snapshot, especially to a stakeholder, so that they can take a quick snapshot look at this and really be able to understand the information. For example, when I look at this, I can see that the group E marks, or I should say values, are higher than most of the other groups. So we also know that they're either meeting or just under the benchmark for every variable. So something's going right with that group. Now, we do have a problem with p-values as they appear in larger data sets, okay? So as a data set becomes larger, the more likely the p-value will highlight significance for minimal differences, okay? So it just basically becomes more and more sensitive, all right? So the problem here is that it may show minimal differences between the groups and show them as significant, and that they would not naturally occur. Now, this isn't always, I'm going to say, technically correct, as we will get minor variations that occur by chance. However, due to the sensitivity of the p-values in very, very large data, we just have to be aware and be ready to handle this, okay? Now, we have the exact opposite problem with smaller sample sizes. With smaller sample sizes, basically larger differences are going to be required to identify statistical significance. This may be larger than is either possible, or it's going to be so insensitive to the change that you're not going to get an adequate reading on a statistically significant change, right? If I measure something in a very small sample size and I have a true significant change, I may actually miss that finding and I may report it as statistically insignificant because my sample size was so small. So you can kind of see there's a sweet spot for the sample size that we utilize with our studies. For randomized controlled trials, the minimum sample size is typically 30. So there's kind of the first key benchmark that we want to meet with sample size. They typically say the larger the better, but just be aware that the larger you get, the more sensitive the test becomes. Okay, as it gets larger, one thing that's going to be of more significance, possibly to your conclusions, is something called clinical or practical significance. Okay, so clinical significance, it's basically the health outcome change that in the perspective of a practitioner or an expert has been identified as important, and you should pay attention to that change. All right. Now, this can occur outside of statistical significance. Essentially, you're going to ask an expert if this value of change is of interest. Is this important? So, for example, I don't expect many of you to be familiar with the DAS-21. Basically, it's a tool that's used to measure mental health symptoms, and it has 3 scales: depression, anxiety, and stress. Now, I've used this tool in regard to the anxiety measurements, and it has different cutoff points for example, low stress or normal stress, mild, moderate, and severe, right? And there's a certain range in between each. Now, you can have values on that tool that might not show statistical significance. For example, I might have a change in value that puts a population, or a sample, I should say, going from in mild to just under normal, but that change won't be statistically significant due to my sample size. Okay, it wasn't large enough to it's undersensitive for the test. Okay, now clinically though, that's a significant change, going from mild to normal. Okay, now I can't make that distinction myself. I would need the help of an expert in the area, so just bear that in mind. Okay, the reason I need that expert is because there are a few standards that exist that are able to determine clinical significance, so you have to rely on that practitioner expertise. I have to ask someone else. Okay, there are ways where standard deviation may sometimes be used. I'll be honest, I have never used these methods. I have always consulted with an expert in the field, and they've validated whether it's been clinically significant or not. Now, one approach that is gaining popularity is something called the integrated knowledge translation approach. This is something I have used. Basically, what you're doing is you're incorporating a group of stakeholders, which more than likely will include experts on the panel, and you're including them throughout the duration of the study or the evaluation. That means that you're consulting them right from your initial questions to your data collection methodology and design, as well as the interpretations of the findings. All right, so you have that clinical significance throughout the entire process that you can rely on. So that may be one avenue of approach that may be of interest to you. Okay, so next up are associations. Associations allow for the determination of a relationship between 2 variables. How do they interact with one another? How are they associated? What does one do in relation to the other? This includes correlations, regressions, survival analysis, and crosstabs and chi-squares. Okay, so I do want to note one thing here. In your book, it says that correlation values are between values of 0 and 1. That's not entirely true. If you've taken a stats course, you understand why, but we're going to review it here. So basically what the correlation is doing is it's looking at the mutual relationship that describes the degree of relation between values of -1 and 1. And essentially, the negative values tell you the direction of the relationship. Okay, so let's dive into that a little bit more. If you have an R value of 0, so a correlation equal to 0, that just means there's no relationship at all. That's what we see here in the top right graph, where you have that horizontal line of best fit. There's no relation between the two variables that we're looking at. If you have a value of -1, okay, what you're getting is a negative correlation. Now, this means that as one variable increases in value, the other one is going to decrease. This is what we see in the top left corner. You'll see how that line of best fit is going down towards the x-axis. That is a negative correlation, and this is the only thing that the negative value denotes. So I can understand why the book said values between 0 and 1. However, that negative value is important. Lastly, we do have correlation value that equals 1. This is a positive relationship between two variables. So as the value of one variable increases, so does the value of the second variable. Now, that value, so either between 0 and -1 or 0 and 1, is going to tell you the inclination or the decline of the slope. Okay, that's the value of the slope of that line of best fit. It tells you how related things are. Okay, so the closer you get to 0, the less of a relationship they have. The more you get to 1 or -1, the more perfect of a correlation that exists. Okay. Now, regression analysis also use lines of best fit to determine a correlation. However, what regression allows you to do is it allows you to work with multiple variables. Okay, so it's going to help to control for those confounding variables that we talked about previously. So essentially very similar to the idea of correlation. However, the big difference, correlation, you're dealing with two variables. Regression, you can deal with two and more. All right, so next up we have survival analysis. So survival analysis is a technique used to study the length of time to occurrence of an event. So it's basically the probability of the event at any point is estimated from the cumulative probability of the event of each of the preceding time intervals, right? So everything is broken down by time interval with the probability that the event will occur in that time sequence, and then an additional probability is generated. So the precision is dependent on the number of observations made. Okay, so think of it as essentially when you're thinking of collecting data points, think of it as like number of participants. The bigger the sample size, the better. This is done through the use of Kaplan-Meier curves. All right, so the last thing we have to talk about is generalizability. So generalizability basically is that applicability to as broad a group of people as possible. So obviously you can't sample the entire population, so you want to get a sample that's representative of that population so we can infer that the findings will also apply to them. All right, so this is why we always want to emphasize that our results can be applied to the real world or a larger group of people. Now, the big thing to keep in mind, design your study with the greatest external validity as possible, because results with greater external validity are also prone to be more generalizable to the setting and population from which that study sample is drawn from. Okay. Now, the big thing here, we can improve our generalizability by performing multiple studies of different demographics in order to capture a larger sample that is more representative of a broader population, right? This relatively common sense, if you think about it, the more groups you can include in your study, the more it will apply to kind of that broad spectrum population. Now, we must always take care to respect and adhere to the limitations of a study itself, okay? Studies will always have limitations. The statistical tests we use will always have limitations, and especially our interpretations. So we have to respect these limitations, we have to report them, and we have to be honest about them.
All right, and that's it for this week. It was a shorter lecture week compared to the other ones, but that's not a bad thing. With that in mind, I do suggest spending a little bit of extra time on your assignments. Remember, if you use RStudio or Power BI for your assignment too, you do get bonus marks. You get a bonus 5%. So just keep that in mind. If you do have any questions, please let me know ahead of time, and I am more than happy to meet with you via Google Meets and discuss them. Have a good week.